and welcome to you all. It's great to have you here. I briefly saw there's 63 people in the chat. That's brilliant. Obviously, neuromorphic technologies is quite a hot topic, and it's actually the topic that in APL Machine Learning we have been featuring since the launch. Probably half of the scope of the journal is dedicated for the neuromorphic and the intelligence systems, so various kinds, future computing, and so on. So my name is Adnan Mehonic. I'm editor-in-chief of APL Machine Learning. I'm also a professor here at University College London. London is quite hot today, so we've been just discussing that. So I'm delighted to actually have quite distinguished members on the panel that are going to give talks, and then you're going to have some opportunities for the questions. You can drop your questions in the chat. I believe they're going to reach me at some point. So what I'm going to do very briefly to introduce our panelists. They really have a long list of accolades, so there's no way I can read all of those. So please do check them out yourself. But I'm going to start with the Professor Beatriz Noheda. Beatriz is a professor at the University of Groningen in Netherlands. She chairs a solid-state materials for electronics group. She is also the founding director of Groningen Cognitive Systems and Materials Center. This is a multidisciplinary center dedicated for the novel materials, devices, circuit systems, and architectures needed to create brain-inspired computers. So very relevant for the topic of today's webinar. Beatriz is also a fellow of American Physical Society and a recipient of IEEE Robert E. Newman Ferroelectrics Award. She's the author of more than 150 publications. So welcome, Beatriz. Great to have you with us today. Then our second panelist is the Giulia D'Angelo. So Giulia is assistant professor at Czech Technical University in Prague. She works on development of neuromorphic algorithms for active vision. Her education spans across many different universities. I believe the University of Genoa, King's College London, University of Manchester. She's also a recipient of Maria Curie Postdoctoral Fellowship, which enabled her to work on bridging bio-inspired software and neuromorphic hardware. And her research today aims to enable robust, efficient perceptron and control for low power, low latency autonomous systems. Welcome, Giulia. And then we have our third speaker, Dr. Petrut Bogdan. He is a neuromorphic architect at Inatera Nanosystems in the Netherlands as well. He focuses on the system architecture and product development. He currently chairs the Neuromorphic Working Group at the Edge AI Foundation, which aims to address the grand challenges within the neuromorphic computing by bridging together industrial and academic experts. Dr. Bogdan also holds the degrees from University of Manchester, and he has a vast experience on working on Spinnaker, that is the neuromorphic system, the largest neuromorphic system for a very long time. I'm not sure if it's still, but yeah, it's one of the most prominent. So welcome, Petrut, as well. And without further ado, I will invite Beatriz to start first with her presentation. Thank you.
Can everyone hear me and see the presentation?
Yes, we do.
Yes? Very good. Well, thank you very much. It's a pleasure for me to be here. I am very grateful to Adnan and the other organizers to invite me here, and I have the honor to start. So I will start a little bit of high level, and hopefully I can go to more details in the 15 minutes that we have in front. So indeed, the title of this talk is The Matter of Future Computers. I'm Beatriz Noheda from the Sereneke Institute for Advanced Materials in the University of Groningen in the Netherlands and from the Cognition Center. So I like to start discussing what's the matter with our current computers, actually. And let me see, this moves. And well, I think most of you know what the matter is. The AI revolution is showing the big energy problem that data centers now have. And one can see that things that we will not imagine maybe 5 or 10 years ago are happening. Microsoft needs a full nuclear plant to power their data centers. Here a quote for the DOE that some data centers are consuming so much energy that they could power 80,000 US homes. That's probably 120,000 European homes. This is really something very serious we need to really tackle and discuss. And I hope we don't get used to this being the norm. And why is that? We also know why this is. I have some difficulties. Is because we are producing and processing and consuming enormous amounts of data, and our computers are not designed for that. We don't criticize von Neumann. The times have changed tremendously. Our computers are a half-century-old design, and it does not really function well for what we now need for the AI revolution. And the problem, as you know, is this von Neumann bottleneck, the separation of processor and memory, and the huge traffic of data in the bus gives rise to not only very high power consumption, but also very high transmission latency. And this is a big problem that we are facing at the moment. But in the future, we want even more data. We want autonomous driving. We want personalized medicine. We want sensors everywhere that tell us how well we are doing. And we want these sensors to respond very fast and to take decisions very fast. And it's not only about energy that will keep on increasingly, exponentially increasing, but it's also about issues of latency and also privacy of this. So sending all this data to the cloud. And I think Petrut Bogdan from Inatura is going to talk much more about this. We really want to do edge computing. We really want to compute at the sensor, and this means with limited resources. So how we can do this? What is the solution for this to revert this energy consumption in computing without having to use less data or to change the dreams that we have for the future? And the solution is called differently by different people: brain-inspired, neuromorphic, in-memory, in-material computing. But basically, it's taking inspiration from the way the human brain processes information. We are constantly bombarded by a lot of the sensory data, and our brain is able to process this data in a very energy efficient manner. And solutions that actually take inspiration from the brain have shown already energy savings that are 3 orders of magnitude, 4 orders of magnitude or more. So this can really be a game changer. And why is that? It's not a mystery. We actually understand pretty well why this happens, because there are very key principles of computation in the brain that can very easily account for these energy savings. You can see here in this beautiful paper by Cathy Schumann and collaborators what are these main differences between our von Neumann architectures and the brain, sequential processing versus parallel processing, and these other characteristics that are taken into account now in the neuromorphic chips that people are designing, and you will hear that later also. Mainly asynchronous, event-driven versus synchronous computing, using spikes and analog communication, but very importantly also co-localization of processing and memory in the same device, in the same place, or as close as possible together. So these neuromorphic chips that are around are several. This is not an exhaustive list, but they take the chips that are now existing, they take some one or more of these principles into account to demonstrate very energy efficient task compared to our current computers. You can see here some of these chips are experimental chips. Some of them are actually commercial products, as you will hear later. And the field is really booming, and there are breakthroughs, as you will see later on with Inaterra and others, that are really giving us the direction for the future. But what those chips need, different developments for the future. For example, scaling and versatility could be improved. And for that, we are thinking of how to go in the direction of better, more efficient, more scalable, and more versatile neuromorphic chips. And for that, the idea is to develop membristive devices, to include membristive devices in the chip. And what are membristive devices? These are 2-terminal devices, sometimes 3-terminal devices that, like resistors, they follow Ohm's law, but they have variable resistance that are changing when the charge passes through the device. And the typical characteristic we want to see in this memristor is a highly nonlinear and hysteretic resistance versus voltage characteristic that can allow for multi-value and non-volatile resistance, as you can see here in this sketch. If you have these devices, you can actually co-localize the data processing and the storage in a device which is nanometer scale. The IV characteristics of these devices have this very particular, what we call a pinch loop, and they are made of either typically a semiconductor or an insulator, very thin layer sandwiched between two electrodes. And what you want to do with these devices is to change the conductivity, to change the resistance at will with the number of voltage pulses, either increasing or decreasing the resistance. And in this way, we do signal potentiation or depression, which is exactly what synapses, the connection between neurons in our brain, are doing. They are potentiating or depressing the signal at the same time as they create memories. So these kind of devices can offer the memory and the plasticity that we need to emulate the brain in a single device at the nanometer scale. And that will be the goal of our future computers. So what is actually the matter in these memristors? And the matter inside these memristors is actually very diverse. You have materials and physical processes that are very that can vary from molecular switchers to valence change materials to magnetic systems to ferroelectric systems. And here these are typically the same kind of physical processes that people have been investigated already for a while for emergent RAM memory. But in the case of memoristic material, one needs to control even further to create all kinds of intermediate states. So higher control of materials. And here you can see some examples, already some of them quite old. So the field is really evolving very fast and already is quite mature. You can see different phase change materials, chalcogenides, for example, or redox-based materials, oxides, or magnetic materials, magnetoresistive systems that can offer these multiple resistance states, multiple non-volatile resistance states. Ferroelectric materials can also show membristic behavior when, for example, introducing a tunnel junction with a very thin layer of a ferroelectric in between two electrodes. One can map the polarization state, which you can see here by the number of ferroelectric domains that are switching up or down. This is shown by the color here in this circle. You can see the number of domains is switching from up to down, and concomitantly with that, the resistance of the ferroelectric tunnel junction is changing, and you can see that this behaves as a memristor. So more or less at the same time, 2011, Kimonda discovered that hafnia could be also ferroelectric at the nanoscale. And this has revolutionized the field of ferroelectrics because this hafnia, of course, as you know, is silicon compatible. So you can already incorporate ferroelectric hafnia in CMOS. And this has increased the number of research and applications, including ferroelectric materials, enormously. So people working at Kimonda moved to NAMLab, and this is where most of the work, original work on ferroelectric hafnia happened. But nowadays, hundreds of groups all over the world are working on these materials and developing fantastic ferroelectric devices. And the ferroelectric memory company has recently got 100 million euros to develop ferroelectric transistors. So this is now in the market, ferroelectric devices, and is actually a great revolution. But what do we need to go from a binary memory to a members device is actually to increase the materials control tremendously from crystal perfection, so crystalline perfection that we need in a ferroelectric material to get to 0-1 states, to control the defect selectivity, for example, or to control the symmetry of the material by strain engineering in a very, very precise manner. So materials engineering is tremendously important, and that's why epitaxial oxides become really relevant in this field, because you can have a lot of diversity on the functionality with materials that are of this type, perovskite materials of the AB type, where you can use different cations for A and B and create materials that are from insulating to conducting, from ferroelectric to magnetic, and you can do a strain engineering with them. You can create electrostructures with perfect interfaces, but mostly this was done at too high growth temperatures that are not CMOS compatible. Things are changing quite a lot. This is a work by Henry Sønsteby in the University of Oslo, where they demonstrated already some time ago that you can actually create epitaxial perovskites at CMOS compatible temperature by atomic layer deposition, which is the technique of choice for chip fabrication. This is we are part of this concept project together with Henrik to actually develop and expand this possibility to other materials like ferroelectric. So this is something that is happening actually. But there is also heterogeneous integration that more and more we need heterogeneous integration for MEMS, for optoelectronics, and this is less of a problem. Flip chip and other techniques are very mature already. So it's time to do this. It's time to go to other materials that are more exotic. And here I want to show some examples from my group. With the hafnia ferroelectric material, because of the very large energy band gap, one can get devices that are only 1.5 nanometers thick, and still you can have robust standalone devices, ferroelectric tunnel junctions that were not possible with other ferroelectric materials, as you can see here. So this is a great development in the field, this hafnia ferroelectric material. Recently, we had, together with Martin Sarot and Yintian Zhao in the group, we were able to deposit barium titanate, ferroelectric barium titanate on silicon using this buffer layer, strontium stanate titanate that was developed by Ruben and Ewout, also in my group. And if you see, compared with hafnia, the switching field of barium titanate is 100 times even less than the switching field of hafnia. So for low power applications, switching voltage of 0.35 can be achieved with very low imprint, which is a big issue in this field. Next to synapses, one can also develop neurons, and this is a work that is done by Piquet collaborators and many others, by the group in San Diego, also on what we call threshold volatile memristors. So these are typically transition metal oxides that have this threshold to show memristic behavior. So with these materials, combination of these devices, one can actually emulate action potentials in neurons. The problem with this is that local heat in these materials can change the balance state and change the behavior very easily. So for that, also perovskite materials like MOT insulators and nickelates are very interesting. And this is also something that we are doing in our group together with Pavan Nukala, who is now in Bangalore. And what is very nice to see is that one can actually, because of these heterostructures and perfect interfaces in epitaxial oxides, one can actually combine the synaptic behavior of a ferroelectric with the switching behavior of a MOT insulator by this kind of combo devices, in which, depending on the direction of the ferroelectric, the system can behave as a neuron or as a synapse, as we demonstrate in this work here. So you can have an oscillating device acting as a neuron when the polarization of the barium titanate is switched up, and you can have a synaptic material working as a non-volatile memory when the polarization is switched down. So in conclusion, membristic devices will allow further advances in the next generation of brain-inspired computers. We have a need to harness the whole variety of available materials and physical properties, and the timing is excellent because heterogeneous integration is maturing really fast. Also, epitaxial ALD is developing in new directions, with strain engineering being possible. And with the discovery of ferroelectricity in Hafnia, the field is showing a great promise, also showing these materials as good memory stores. But other materials like barium titanate and other perovskites are also very interesting, even for compact combined functions, neuron or synapses. And with that, I would like to acknowledge my group and the funding agencies, and I would like to thank you for your attention.
Great, fantastic. Thank you, Beatriz. Really nice overview. And I think that lends us quite nicely to Giulia's talk, which I believe is going to be some combination between software and hardware. So, Giulia.
Okay, I had to unmute myself. Can you see my slides?
We do, yes.
Perfect. Okay, I'll try to rush it. I need to put the time in front of me. So hello everyone, and thanks for having me. I'm super happy to be here. Now, what we do today and what I will try to rush today is the concept of what catching your eyes and why you look in certain places rather than the others. Okay, here you have a bunch of angels. I call them angels, and these are all of my students with me. I don't have to repeat my background, and now I'm currently funded by the National Gutcher Standard Grant. So let's start now. Thanks, Beatriz, because she said basically everything I needed, and I don't have to repeat myself. So the idea that we do need to spend less energy, I think it's clear now. And I want to add another problem. The media are basically telling us that we have robots in our apartments, or the robots are ready to enter our homes. It's not true. We know it. It's not going to happen now. And the problem is because they cannot move in an unconstrained environment. They use too much energy and too much latency, so they don't react effectively. Now, I don't have to convince you for today that someone has already done it. So nature has already solved these problems for us, right? We have a bunch of examples here playing around, and me, for example, in this moment that I'm talking, I'm trying to do everything correctly. I'm set here in my room, and I'm trying to be very, very fast for this talk. I use 20 watts, or at least this is what Steve has said many years ago. Now it seems to be a little bit debatable, but still the idea that we use a very teeny tiny energy, it's still there. So what I do is neuromorphic sensing and computing that you all know. Now, let's go back to the concept of how do we define attention. If I ask you what is attention for you, you intuitively would know what does that mean. But if I ask you to define it, that's not easy, right? It's not easy to explain it. So in this case, what I have to do is to tell the robot, look, in this specific context, forget about everything else and look at the candle because the cat is about to burn, right? It's not easy. So let's look at this video for 1 second. Perfect. I cannot ask you questions, but I can tell you that what we are seeing is a person that it's typing and then it's responding to the phone, right? Perfect. The problem is that these are two completely different people, right? You haven't seen it. Fine. The brain is doing exactly what it should do. It's focusing the attention on what is important, which is the context and which is the informative information of this video. There's someone that is typing and then is taking the phone. Fine. Now, this question is part of a question from Jarbus Alfred, 1967, where he was looking at the eyes and motion in the scene, looking at different scenes, right? With giving a task, sometimes in free viewing. What we can see here, I hope you can see my mouse, what we can see here is that we jump from one head to another one, we look at the figure, and if I would ask you, which I usually do in my talks, what is going on here, the real truth is that here we are nosing the situation. So we are trying to understand what's going on. What is the social interaction between them? If they're fighting, if they're talking, and so on and so forth. In this case, we do triangulation. And in this case, we look for the foliage, and then we see this high contrast figure, which is a bear, right? So it's not easy to understand where we move our eyes around. We can collectively have some patterns if we look at different subjects looking at the scenes, but it's not easy to explain exactly why and how to model it. So we have understood that these movements are the eyes in motion in the scene, and this is called scan path. And then on top of the scan path, we can have a saliency map, which is telling us what could be attractive in the scene. But how do we obtain this saliency map? Well, in 1998, these three people that you find here, and one of is here with us at the Canadian Neuromorphic Engineering workshop, they came out with this idea to get a bottom-up, completely bottom-up feature extraction saliency map, trying to extract the features of color, intensity, and orientation, so you can do it in a different way, to obtain a saliency map, a visual saliency map, to tell us where we should put our attention, so how we should move our attention. Again, completely bottom-up. And this is super cool, but feature extraction is definitely not enough. Perfect. What do we add then? So if I ask you here, what's inside here, you would certainly say, this is a dog, this is a square, this is a triangle. But it's not, right? So what the brain is doing here is perceptually grouping the information in the scene, right? This is a closure principle, and it comes from the Gestalt principles. The Gestalt principles are around 1938, 1950s, and what they're trying to give you is perceptual rules of grouping the information from the visual scene. So we have the closure, trying to perceptually group edges that are close to each other, and you can see corners that are close to each other and facing towards each other. Then we have the figure ground organization, the similarity, which is basically trying to group instinctively things that are of the same shape, and proximity. Okay, we group things for proximity. Now, why this should be interesting? Well, because then in 2000, Zhu et al. Found some cells in our brain, and I do stick with biology a lot. I do stick with bioinspiration a lot in my algorithms. What they have done is that they found these nice cells, you can see it here, that regardless of the color, background, foreground, you can see that they have a huge activity when the object is on the left. Okay. How come? Well, in V1, we have amazing filters that are called Gabor filters. And what they do is that you can see that there is an excitatory part, an inhibitory part, and they react to edges orientation. But then if you group the information together, then the grouping cell understands that there might be an object. Right? So instead of just doing plain feature extraction, colors, intensity, and so on, we can also visually group the information in the scene to see if we can detect blur blobs in the scene where we think there might be an object. Okay, so it's a step before the object recognition. This is called a proto-object, and is an object to be. Right? I just said is not an object. We think that it's an area that might contain an object. And this is what Ralph Etienne Cummings and Russell et al. Have done, adding to the model of Ernest Niebuhr, Christoph Koch, and Lauren Itti. They added this border ownership pyramids and grouping pyramid. Why border ownership? Because these cells are called border ownership, right? They give you the ownership of that edge. Perfect. Is this just fancy by inspiration? This is just an intro to let you understand how I started my PhD, right? And this is the question I asked myself. Okay, how do I use all of these bio-inspired algorithms to do something into the 3D world for us? And this was iCub, the robot that I started using at the start of my PhD. So then I started from this model and I choose three different channels of information. Intensity was coming for free from the cameras. Be mindful, we have even-based cameras in the eyes of iCub at IIT in the ADPR lab, which is led by Chiara Bartolozzi. Then what I wanted to add is the channel for depth, because if the robot needs to interact with something in the scene, then we need to know the depth of the objects around. And motion, because it's inherently interesting, is an alertness signal. Fine. This is what I managed then to do during my PhD. So we have some cool applications here running online on iCub. We have the events and then we process the events. And here you have the saliency map. And then you can see that the attention is on the mouse, is completely disregarding this line. Lines are not objects for us because they're not close contours. In this case, what you can see here, and I'm gonna stop it here 1 second, we have two objects here, right? So it's very difficult for the robot to decide what to grasp. And what happens is that if you input the depth information, which you should look here, then it focuses only on the object that is the closest one. And the motion channel, it's part of the spiking elementary motion detector, and it's working on Spinnaker. I need to go super fast, so I cannot really tell you about these results. I compare, my ground truth are humans, so it's not super easy, but it's a good validation. Now, to go on, I asked myself how we can segment, how we can get the figure ground, and this is another publication. Is just you can check out the publication. I will go on for the sake of time. Now, the point that I want to give you today is, if you look at this model, this is running 100 milliseconds on a GPU, 170 milliseconds on a GPU. Look at here. These are implemented on Spinnaker, and these are the same model, the intensity channel on a GPU and the intensity channel on Spinnaker, 16 milliseconds of latency. Of course, drawback, I had to use 6 boards, which is unfeasible. This is another recent publication with Luca that we are working on, trying to get a very fast ROI detection. Now, I want to go super fast because I think I have like 3-4 minutes. Visual attention, of course, was what I've done during my PhD, but then I started to be obsessed about what is going on in our retina. Our retina is doing plenty of things for us. For example, distinguishing what is emotion and what is not emotion during microsaccades. So the eyes are in constant motion. And the problem is that when you move the camera, you don't understand anymore what are the events from the static scenario and what are the events from the dynamic scenario. But now, yes. And this is exactly what the amacrine cells do. They look for contrast motion in locality. You can see that here we have the input, which are events, and you can see the static scenario. And here you have the information only of what is in motion, which is my hand, right? Now, the cool part of this, from the engineering point of view, is that we reduced off the 85% the incoming events. And if you work in active vision, that's a very good thing to have. Now, many results. I'm not going to go in forward. You trust me, you will look at the publication and you will see that we had nice intersection over union and structure or similarity with ground truth. Now, the point here is that this is an entire loop, right? You have the events are coming into the object motion sensitivity, so we are distinguishing what is in motion in the scene, and then I put on top the attention. Then I have a point of attention, I feed it into the Nango control, just a P controller, and what I get out is U-pan and U-tilt to put the object in motion, or the interesting object, salient object, whatever, you put it in the center of the visual field. Now, to continue the loop, you will go again with fixational eye movements. You don't know, but you are constantly moving your eyes. What happens is that they jitter a little bit here, you acquire the information, and then you saccade, you move your eyes towards the next point. So the idea is that embodiment is very important. And it's not just a buzzword, because here, if I remove this part of the fixational eye movements, this model is not going to work anymore because it works in locality. So there is a reason of every single step in our early visual system. And I proved it here, right? Fine, let's go on. This is how it works. You can see that it's working online. And I know that this talk is about machine learning, but I'm actually happy to tell you that here there is not a single line of learning, because we don't need it for things that are that easy. Learning is something that we need to use when we need to do very complex things. This is working as it is, just following the structure of nature. And it's working on my Mac, 120 milliseconds, and on the spec version, where we have 1 milliseconds and 1 watt of power consumption, which is what I'm doing with my buddies here. So I have two computing part, one is on the Mac and one is on the spec. And the difference, of course, is not even comparable, because in one case we have only 1 watt of power consumption. And here we are trying to integrate in near multi-neuromorphic platforms to do vision on the spec and the control part on Spinnaker. Now, just to give you the last point, which I think I need to go, what I want to do now is to encode with the eyes in motion the classification of the object itself. So what I want to have is the experience of the observer that classifies the object, so that I do not need a gazillion data, but I will just rather acquire the experience of the observer. Fine. I'm going super fast. I need to close. This is part of a bigger problem, which is not just vision, but it's skin, touch, proprioception, and so on and so forth. So we came out with a benchmarking framework for embodied neuromorphic agents, which, if you have time, let me know what you think. And then this is what we achieved so far. So these are all of the applications that we have done. This is a robot that it's painting after a painter. This is end-to-end spiking neural network on Dynaps using the DVS. This is coastline detection in 20 milliseconds with 0.3 milliwatts of power consumption on Spinnaker. And these are the latest things that I have done. Sign language recognition, 92.27 accuracy deployed on Spinnaker with 0.5 milliwatts per consumption. This is a spike neural network playing pinball, and it plays way better than the humans that are my students, 148 microwatts. This is the application that you have just seen. Then I'm trying to modulate the attention with the keyword spotting on FPGA. And this is eye blinking and eye tracking using event-based cameras with 3 milliseconds latency. So thank you so much. I tried to rush it a little bit too much, but please do get in touch if you want to know more. And these are my guys.
Thank you very much, Giulia. That was a great talk. Really, really nice. So the last speaker, Petrut, no pressure, but we are running a little bit late on time. So not only if you can stick to the time, but maybe save us a couple of minutes, that would be amazing. But yeah, please go ahead.
I'm on it. Hi, everyone. I generally go by Peter, and I'm going to talk to you a bit about what we do at Tenaterra and how we see neuromorphics changing the world in terms of edge processing, sensor edge processing. So quickly, we are a company that spun off from TU Delft, so it has academic roots. We have over 110 employees. We might actually be 120-ish maybe employees at the moment. And we're hyper focused on creating not just accelerators for spiking neural networks, but microcontrollers, which you can see multiple generations of in the bottom right corner, and you can't see my mouse, so we move on. What is the problem? The problem is that, well, the opportunity is that there are sensors everywhere. There are so many sensors in all of the devices that we're using all over the place. And so this means that the sensor modalities are very varied, and the interfaces required to interface with these sensors are also quite varied. the numbers of these sensors overall as volume, not just per device, is also absolutely insane. And as a market capitalization, you can see why we're mainly focusing on this sensor market, making sensors smarter at this very moment. The gist of it is, if you have so many sensors that are produced and deployed on the market in real deployments in the world, then this becomes a problem that cloud infrastructure providers have also identified. There's a lot of data that you would have to, the alternative of not you doing edge processing would be to send data to the cloud, and that is a lot of data, and therefore ties in very neatly to what the previous two speakers have also mentioned. So from the Beatriz's perspective, the power is very relevant. From Giulia's perspective, very likely the latency is a problem. The round time to go to a data center to do some processing may be too much for certain applications. So where we're trying to slot in is that generally in the signal processing value chain, you start with a sensor that can be for consumer electronic applications, generally consuming less than a milliwatt, that are connected to microcontrollers that generally consume up to 10 milliwatts-ish. But these systems don't have a lot of compute available on them. They mostly rely on software. They're relatively simple devices. So as soon as you want to do any more complex operations, you need to go to systems that are more power hungry and larger and further away, and therefore increasing power and latency as you go to the right. So we've announced quite a while ago, I don't remember exactly when, we've announced our mass production microcontroller called Pulsar. The spiking neural processor, so it's a neuromorphic microcontroller to address that gap that we see in the market related to the ability of these microcontrollers, the first chip that a sensor talks to. So we've created Pulsar, which is a heterogeneous system on chip that features front and center SNN accelerators for bringing down the power of inferences that our customers and that we perform on the device, while also building generic infrastructure around these spiking neural network accelerators to support a very wide range of applications that our customers are looking for. So as you can see, namely to point out the interfaces, I was talking about the variety and the number of sensors that exist on the market. And so we've equipped our system to be able to deal with a lot of these sensors and to be able to do typical digital signal processing or typical neural network workloads to be run on the device, apart from and not just SNNs, because we believe that there's a synergy between the more traditional approaches and SNNs. I can talk more about this later in the more free-form section, but basically what we're working with our customers on are in the pillars of consumer electronics, but also IoT and smart home, industrial application and wearables, with some of the example applications that you can see here. In this particular talk, I'm just going to shout out one of the audio applications, one of the audio products that are coming out soon. But first, in order to our ethos is that in order to make neuromorphics accessible and to be more widely adopted, the software flow, the application development flow has to be very clean, very easy. You should not require a PhD to be able to deploy an application on one of these microcontrollers. So we've created a software toolkit called Talamo that allows users to define not just models, not just neural networks, but an entire signal processing pipeline directly in PyTorch or very close to PyTorch, and train the entire pipeline end to end and see the results on data that you already have. You can check in simulation, or you can check on hardware directly. Obviously, in order to go to hardware and actually embed one of these signal processing pipelines and neural networks that are running on a PC and with float weights. You need to follow some steps. You need to do quantization. So we provide a lot of you need to do quantization, to do code generation from software that runs on your PC to something that can be run through a generic RISC-V compiler to then put on the device. You need device drivers, etc. So we provide the entire stack from the software that runs on your machine and light greenish, yellowish, to blue that is device levels or firmware. Firmware that runs on the device, and then the types of hardware that you can target with this entire flow. I'm not gonna go into a lot of detail. I promised you I'd talk a bit about one of the products that are coming out that have been announced with our customer Giulia Design. They're working on a smart baby monitor. It's cool that the tech has advanced enough nowadays that it's no longer just a battery operated baby monitor that you take with you, leave one in the room and then take the other one with you that tells you when the baby's crying. But this one also tells you why is the baby crying. So this is looking forward to seeing the baby translator out in the world, so you can already go in the room prepared for this baby crying because of hunger or some pain-related complaints. More generally, and also zooming out a bit, what is also important, we feel from a neuromorphic perspective and from the adoption of neuromorphic systems, is not just producing the chips or the software. It's also important to give customers what we call application architecture. So model zoo, a lot of customers don't understand the relationship between a typical neural network or a CNN and architectures that are neuromorphic, let's say. So there isn't an immediate understanding of how architectures map between the two systems. They also require fast time to market. Therefore, we also provide a lot of data capture tools and annotation tools for the data that they grab. But also we want to work a lot more on the developer ecosystem, because that is very important in order to have adoption of any of these systems. You need a critical mass of developers. So we're pushing hard for a developer program that I believe should be coming out. I don't know if this, I don't know when we are, but should be coming out soon. I think I've been saying this for a while, but now it's for real. So in the next couple of months, rolling out our developer program for users of the chip, but also more closer to my heart, a model repository for dedicated to spike neural networks. So working on the interoperability side of SNNs and where you can deploy them. So that so we built this tool, this platform called Synfire, where it's community, it's for the community, so it's not platform specific. It's not for Inateras chips. It's for all chips that are neuromorphic, using at the moment the neuromorphic intermediate representation to describe the models, but working on with the community to expand this to other ways of representing SNN models to be able to run them on various devices. Time.
Great. Thank you, Petrut. That was on time and great talk indeed. So we don't have many questions in our chat, but we do have one. Okay, there's a few more coming. So the first question we had is on latency. I believe the question was phrased, is neuromorphic computing really with zero latency? I think zero latency would potentially break some laws of physics, but maybe if anybody wants to comment on the latency improvements in general.
I'm unmuted, so I'll start to give everyone else a chance to give a better answer. We've been talking also in this in this series of presentations about the model system that we're using for all of our neuromorphic developments, the brain. The brain isn't just a computing device, it's a predictive device. So zero latency, obviously that I feel doesn't exist, but when it comes to simulating or emulating brains generally, it's important to consider the fact that it's possible to implement prediction algorithms. And if you can, a simple example that I remember from my PhD times is that if the brain expects a particular signal, a particular sound to happen, there are downward pathways that can positively bias, for example, certain frequencies inside the cochlea, so that you're more likely to catch them very early on, and so you decrease the false positive rate, and you have a faster response of the entire system when that stimulus comes. So and neuromorphic as a general term includes a lot, and I just wanted to mention this one because I thought it was cool. But I think Giulia and Beatriz have other very topical answers to this.
So I don't know if Beatriz want to continue, then I can give an abstract point of view from the applications that I do from the robotic world.
No, please go ahead. I think you both are dealing with latency in your daily lives.
Okay, so as Petrut has said, latency is a problem for robotics a lot, in the sense that we want the robot to react very fast and to adapt and lots of things. Of course, full zero latency is impossible, but for example, in all of the applications that I showed, I can have a motion direction detection for 4 milliseconds, a saliency map of attention for 16 milliseconds, coastline detection for 20 milliseconds. And this is impressive because it's way lower than collecting a single RGB frame. So I am able to give a response that maybe doesn't have the same accuracy that RGB word has, but slightly less accuracy. It's uncomparable with this gain on low latency. So latency is important, and specifically for complex robotics. So now we have all of these chunky robots that they move very rigid. But for example, to control a soft octopus robot, then it becomes a problem, and a digital controller cannot cope with that. So we need very teeny tiny latency, and we need to address how to control all of the different parts and all of the non-linearities with a very good controller that does not sync with a huge clock.
Thank you, Giulia. Beatriz, do you want to add anything?
No, thanks. I think it was quite well.
Excellent. I have quite a long question here, because I can't. Please, for the audience, if you can just make your questions sort of brief, 2 lines max. But maybe I'll ask just a couple of questions as we are waiting, and if you can keep it the answer within 1 or 2 minutes, that would be brilliant. So maybe to Giulia, again, coming to the embodied neuromorphic system. So just maybe conceptually, if you can explain what's the conceptual change when we have something like conventional algorithm softwares on a computer, and then when we have something that actually changes perception of the time, interacts with the real world, and maybe it's that embodied piece. Can you help us understand the differences and maybe challenges between the two?
Yeah. So from the engineering point of view, it's a mess because I don't work in simulation because I work with actual robots moving around, and I cannot, like I don't have ground truth unless I try to build it, right? Now, the idea is, I didn't have the time, but the idea is, classical deep learning methods use sensor information to understand that this is a cup, right? This is not what kids do. When a kid, it's very young, it's moving the object on its hands and it's moving the eyes. So we have been biased by the RGB community, which is, I mean, it's not evil, but we have been biased by the RGB idea that everything is static and it's belongs on a frame, which is not true. We move our eyes constantly, and the movements of my eyes that I will move here are completely different. Sorry, I was debugging, from the movements of the eyes on the camera, right? So maybe acquiring a sequence of sensor information and joint information, so the sensory motor sequence in time, gives an egocentric representation of what this object is based on my exploration. Now, the point is, if you see this cup once, you don't have to see it again in different contexts, right? Because it's encoded in you, right? So at the end of the day, and this was the idea of the Marie Curie, I don't know, I took risks. At the end of the day, I'm trying to prove with VSA, so vector symbolic algebra or contrastive learning through time, that this is way better than just feed-forward networks to learn an object if you then need the agent to move in the scene and interact in the scene. It's completely different. Yeah. I hope I
Right.
made
Well,
it clearer.
yeah,
Yeah.
yeah, that was great. It's certainly more brain or biology inspired, so that's for sure, and must be better as well. So there is another question just came in for Petrut. So Petrut, here's a question if you can disclose this one. Actually, I don't know, but somebody asked about the types of devices that you're using in the analog and digital blocks in your chip. So are these sort of novel emerging technologies, or maybe the standard CMOS? I don't know if you can say anything about that.
Again, this is I think publicly disclosed, and generally, so the more industrial focus is obviously towards CMOS. So we are at the moment, the devices that we have are CMOS based, so everything is integrated in one SoC.
I see. Yep, that's clear. So there's another question that I believe this should probably be for Beatriz. So the question, in nature, things do not grow layer by layer as done in labs. The growth of such materials, how can nature be mimicked? So I guess it's related to the what breakthroughs we need on materials, and then how does that fit holistically with these neuromorphic or intelligent systems?
Yes, so it's true. We are not aiming in general to do wet matter and emulate the matter in the brain. We know that the brain is very complex with all kinds of neurotransmitters and chemistry and so on that we don't understand. But the part that we do understand, the part that is more mechanical or architectural, is already saving, we know is already saving lots of energy. So it will be too disruptive to go to wet soft matter for microelectronic devices. I think what we are trying to do now is to use what we can actually in microelectronics, emulating the brain, and this is the idea now. And the breakthroughs that are needed are actually quite important, but we are very close by. So 20 years ago, the aim or the goal of the aim of material scientists was to have atomic control, to grow materials layer by layer, atomic layer by atomic layer. Now this is done. We do that in hundreds of labs in the world. We have the techniques to do that. The next step is this control these very complex energy landscapes that we need to create to have memory, permanent memory, memory for 10 years, at the same time as processing, the flexibility necessary to have this plasticity and the processing of information. You need to know exactly where you put your defects. You need to know exactly how you break the symmetry of the crystal. In the case of ferroelectrics, it's a lot about crystal symmetry breaking in exactly the right way. In other materials, it's about which defects you put, how you control them, how you achieve selectivity. You want to go to some energy minima with light. You want to go to other energy minima with electric field to have different inputs, outputs to control exactly when the device is going to be a permanent memory or a long-term memory, a short-term memory. All this diversity that we find in the brain. We are at the moment where we need to control this at the material level. And we can, because we have achieved this atomic control. The next step will be, okay, I'm going to now control the defect landscape and the symmetry landscape in such a way. And this is where the materials field is at the moment in the area of memory-resistive devices. And I have a lot of hopes seeing how things are developing, seeing how the fantastic progress in the past years, that within 5 years we have memory stores really in the market.
Great, thank you, Beatriz. So that actually addressed the two further questions that have been here, because I saw some questions about how reliable or how mature these novel technologies are, including memristors. I'm just going to go with one more question because I believe that's the only as much time as we have. And the question is about the best ways to encode information in spiking or spiking neural networks. So maybe for Petrut or maybe Giulia, I don't know who wants to take this one. But in terms just, yeah, what's different about spiking neural networks and information encoding? Is there the best way to encode it?
The flow that we allow, so the chip, the microcontroller that we've created allows customers to be relatively flexible. There's a lot of debate in the academic community about which encoding techniques are best, which data transformations from multi-bit continuous to event-based single bit or few bit representations, which ones are the best. And the simple answer is it depends. It depends on the application, depends on the sensor modality. So what we've enabled is flexibility and efficiency. We have hardware-based encoders that take data and produce events, but we also have the ability to do a lot of that transformation directly in software and pass the spikes directly to the accelerators to provide this flexibility. And generally speaking, embodying the motto that neuromorphics have a graceful degradation of performance, generally speaking, whether it comes to training over time and online learning and dealing with catastrophic forgetting, or for situations where certain components break down, or for situations where noise is increased on the input side. Or in this particular case, which is much more engineering related, whether you spend a bit more time or a bit more code to encode your data to do feature extraction, then that I would count that towards a graceful degradation of performance.
Great, thank you, Petrut. Yeah, flexibility are certainly one of the main features of biology, brain-inspired approaches, and neuromorphic. So it's great that your chips are made in the same fate. I believe that's all the time we have. So with that, I just want to say a huge thank you to all our panelists and obviously all the people in attendance. Fortunately, we couldn't really address all of your questions. The only other thing I really want to end this webinar with is to check the journal, APL Machine Learning, and obviously for all of you that are working on any level of neuromorphic technologies, to consider the journal to publish your work in. Thank you so much, and have a great rest of your day.
Thank you.
Thank you so much.
Thank you. Bye-bye.
Bye.